two-step problem that we talked about was probably, I don't remember exactly, but it was either mass to number of particles or number of particles to mass. And to do those, you have to convert to moles. So as a general rule, anytime something is given to you that is not moles to start with, you need to convert to moles. Because moles acts as the central piece in your conversions. Once you get to moles, you can go to other things. So we're going to learn 3 conversions in this class, and we've already covered 2 of them. The first one is Avogadro's number, and that is going to allow us to relate number of particles, number of atoms, molecules to moles. And then the second one is going to be molar mass, which relates grams to moles. So anytime you start out with grams going to moles. The third one that we're going to cover today is actually stoichiometry, it's called, which is really a very fancy word for ratios. And we'll talk about that today. But these are the 3 conversions that we'll be doing in this class to keep track of the math and so on. To get our mind started, I came up with a Halloween question, actually. I was just curious to start with. So there's roughly 40 million kids in the United States. Ages between 5 and 12 was the statistic I saw. And over Halloween, 12 billion pieces of candy are given out. So if you do the math, I think that works out to about 300 pieces of candy per kid. Does that sound about right? You get 300 pieces of candy, like single serving packets and so forth in a night? No, I don't know. I ended up with more candy last night than I gave away. So I came out ahead. So our question is this. If we imagine each one of these pieces of candy is a carbon atom, how many grams of carbon would we have? So if you have 12 billion carbon atoms, how many grams of carbon is this? Now 12 billion is actually 1.2 times 10 to the 10th. I'll make. So if you have 1.2 times 10 to the 10th carbon atoms, how many grams of carbon would that actually be? So let's take a minute or two and see if we can work out the math associated with this. Okay, say another 30 seconds or so. Very well. Has everyone got their ideas? No? Okay, so if we start out with atoms, and we want to get to grams, we need to do a conversion, but there's no conversion directly from atoms to grams. So we're going to go from atoms to moles, and then once we have moles, we can then go to grams. So the first conversion is going to be Avogadro's number. Second conversion is going to be molar mass. So we start out then with 1.2 times 10 to the 10th. And we're going to use Avogadro's number as our conversion to get to moles. So 6.02 times 10 to the 23rd atoms goes on bottom. 1 mole goes on top. Atoms cancel, moles match, and we're good to go there. Doing the math, 1.2, 10 divided by 6.02 to the 23rd is 2 times 10 to the minus 14 moles. 2 times 7. Yeah?
Are you going to give us Avogadro's number on the...
Nope. So you need to know that. Okay, so then we have moles, and we are going to move on from there. So then, going to grams, we need to have grams on the top, which means mole goes on the bottom, which is good because it cancels. And what is the number of grams for the molar mass of carbon? 12 or 12.01. I like to do my math a little simpler, so I'm just going to put 12. 12 times 2 times 10 to the minus 14 is going to be 2.4 times 10 to the minus 13. So that's how many grams you would have if every piece of Halloween candy handed out last night in the US was converted to an atom of carbon. So that's obviously very, very small. That's going to be 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2, 4. Very, very, very small mass. Questions about that? Okay. Now, looking out, I see that many of you are just writing it down as I'm doing it. And that's perfectly fine. Not all of you by any means, but some of you are. And that's perfectly fine because you're keeping track of what's going on and so forth. And I encourage you to do that. However, you need to practice this before the exam. This isn't something where you can just watch me doing this up here and then be good to go on the exam. Right? That's not how this works. You've got to practice it. Right? So be forewarned. Okay, let's try one more here. And then we'll move on. Okay. How many molecules of water are in 25 grams of water? So how many molecules of water are in 25 grams of water? Yep. If moles are not given to you, you convert to moles. If you're not sure what to do, convert to moles. If you're copying off your neighbor, what do you hope they do? Convert to moles. Okay? It doesn't matter. Convert to moles is the right answer. And on filling questions where I see what you're actually doing, you can always get partial credit, at least for converting to moles. You never go wrong. most of you probably are. The water is H2O. I didn't use the proper name for it. Okay, let's say 30 seconds or so. Any questions before I start working through it? Okay, here we're going to be doing the reverse, basically, of what we did. We start with grams, and from grams we're going to go to moles, using the molar mass. And then once we're in moles, we can go to a number of molecules, using Avogadro's number. So that's the two steps that to go about getting through this problem. So starting with 25 grams, go to moles, where 1 mole, how many grams is 1 mole equal to for water? 18. 18, because there's 16 grams contributed from oxygen, and then 1 gram from each of the hydrogens. So 16 plus 1 is equal to 18. So 25 divided by 18 is let's just say 1.4. 1.4 moles. 1.4. And then we're going to do the second part to get to the number of molecules. So here, 1 mole is going to be equal to 6.02 times 10 to the 23rd molecules. Mole cancels. 1.4 times 6.02 23rd equals 8.4. 8.4 times 10 to the 23rd. 8.4 times 10 to the 23rd. Does that agree with what you got? What?
I said no, but I understand now.
Okay, good.
So when you're going from grams to moles, you don't need to use Avogadro's number. You need to use the
Molar
mass.
mass. Yep. The relationship between grams and moles is always molar mass. The relationship between number of molecules and moles is always Avogadro's number. Okay, so whenever you see grams, you think molar mass. Whenever you think atoms or molecules, think Avogadro's number. Other questions?
Can you go over that number? Is it 6.02?
6.02 times 10 to the 23rd. That is the number of atoms or molecules in 1 mole, just by definition.
The thing you said before about the converting, you said if you hear these 2 words associated with this, can you say that again?
Okay, so if you hear grams, instantly think molar mass. If you hear atoms or molecules, you need to think Avogadro's number. Okay. Any other questions? Okay. So So we'll come back and do a few more of these types of conversions, but I wanted to introduce the last bit to us. But to introduce the last bit, we have to talk about chemical equations. I know that I've been using chemical equations the entire class. You just can't teach chemistry without talking about or using equations. It doesn't make any sense. But this is the formal part where we describe an equation. So an equation explains what's going on in a chemical change. So early on in the semester, we learned about chemical changes and physical changes. A chemical equation is how a chemist shows what's occurring in a chemical change. So for example, if I have Fe plus Cl2 goes to FeCl2. Now, there's a lot of different ways and a lot of different bits of information that are included in the equation. But the first one is if you make this an imaginary line where your arrow is, it breaks it into before and after the action. So think of the arrow as the verb of your sentence. That's where things are being done. And everything before it is actually before your reaction occurs. And everything after your arrow is after your reaction occurs. So before your reaction occurs, the parts are called reactants, because they're the ones that are going to be doing the reacting. And after is called the product. So reactants are on the left side always. Products are on the right side of your reaction. So very simple question, is iron in this case a product or a reactant? Reactant. Reactant. Okay? Should be the easiest question on the exam for you. All right. Break it up into two. There you go. So that's how we break them up. Now, I can refer to these as reactants and those as products and so forth, and it's fairly straightforward to do. The thing to remember is that reactants are before the reaction occurs, product is after the reaction. So here, for example, is the reaction of silver sulfide, formation of silver sulfide. If you have silverware, like real silverware made out of silver, it gets black and gunky over time. The reason that occurs is the silver reacts with sulfur in the air to form silver sulfide. So here is the chemical reaction for it. Silver plus sulfur forms silver sulfide. Or with just the chemical strips here, the symbols, silver, sulfur is silver sulfide. So that's your basic chemical reaction. Now there are other things we can include as well. I'll come back to that in a second. When you're looking at an equation, we've got pluses and then the arrows and so forth. A plus is basically the same thing as and, or with, or something also. But usually the pluses you can just substitute in and for. You can always just substitute in and for. And then the arrow is yields, or produces, or forms, or something like that. It's the verb of it as you're going through. So if I wanted to read this out loud, CH4 and oxygen yields carbon dioxide and water. So that's how you would say it in English as you're looking at it. You would just substitute an and for the pluses, and yields or something like that for the arrow. So we can go through and write equations in the shorthand chemists use, or we can write them in English. So let's look at another one here. Let's say FeO2 plus 2 Cl2 goes to FeCl2 plus O2. So when I'm going and writing this in English, what I would write is iron. Now iron, if you look to the periodic table, is a transition metal. Okay, so we have to use our Roman numeral. Remember our naming rules for this. So what Roman numeral would go on the iron in this case?
2.
2, and why 2?
Because oxygen has two. It's, I don't know.
Crossover.
Yeah.
Crossover. Okay, so you would bring it there, right? That's not going to work in this case because you can't go backwards like that. Oxygen, if you look to the periodic table, what charge does oxygen have when it's in a compound?
Plus 2. I mean minus 2.
Minus 2. And there are 2 of them, so that's going to be minus 4 overall. So what does the iron have to be to balance that out?
Plus 4.
Plus 4. Plus 4. So this is iron 4 oxide. Iron 4 oxide. And chlorine yields. Now over here, do the same thing. What would the charge on our iron be for FeCl2?
2.
2. Okay. Because Cl is a minus 1, so that's going to give us a minus 2 overall. So that's going to have to be a plus 2 to balance out the charges. So iron 2, chloride, and oxygen. And oxygen. So going from our chemical equation here to the English script version, iron 4 oxide and chlorine yield iron 2 chloride and oxygen. Does that make sense once you see it? Okay, so obviously we can go the other way as well. Let's say copper and oxygen react to form copper 4 oxide. Copper and oxygen react to form copper 4 oxide. So see if on your paper you can write out what this would be as a chemical equation. Copper is Cu on the periodic table. So copper is going to be Cu and is going to be the plus. Oxygen, say O, reacts to form as our arrow. And then copper oxide, CuO. But here, because it's an ionic compound, you have to look at it and make sure that the charges make sense. So if copper is a plus 4, how many oxygens are we going to need to balance that out? 2. 2. Because each oxygen is a minus 2, so that's going to take 2 of them to balance that out. So that's how you would go in the reverse. Yeah.
So, on the reactant side,
Mhm.
oxygen. So you wouldn't put 2 with oxygen.
Okay, let me. Are you talking a coefficient 2 or a subscript 2? A subscript 2 would be okay.
Okay.
Yeah. In this case, because oxygen exists as what's called a diatomic. I'm not introducing that term in this class necessarily, but if you know what that is and it's a 2, then by all means go ahead and do so. Okay. But if you don't put the subscript there, this isn't balanced yet. Okay, and that's actually the next thing we're going to talk about. Yeah.
The explanation for how you got, how you figured out 2 needs to go there.
2 needs to go there.
Yeah, like the charges and stuff.
Okay. So copper has a Roman numeral 4, which means that it's a +4 charge on it. Oxygen, when it's in a compound, is always -2. So to balance those out, it's going to take 2 minus 2s to be equal to the +4. So if, for example, I have Fe, oh wait, let's not do that. Let's say iron, 6 chloride. So iron 6 chloride, what would the formula of that then be? So iron is going to be Fe, and what charge is that going to have on it? +6. Chlorine, when Cl goes into a compound, what charge does Cl always have? -1. So how many of that's going to be needed to balance out those charges? Okay, so if I have a +6 here and a -1, it's going to take 6 of it. So it's going to be Fe Cl6. So in ionic compounds, you always have to balance out the charges. You have to be careful about that whenever you're working with ionic. Covalent compounds, it doesn't matter as much because the names just tell you how many you've got. Mono, di, tri, tetra, and so on. But when you're dealing with ionic ones, then you have to make sure that the charges balance out. Any other questions? Okay. So looking at this equation here, oh wait, yeah, we may as well. Looking at this equation here, there's one other problem with it, and that is that it's not what we call balanced. So how many of you have balanced equations before? At some point, okay. How many of you hated balancing equations before? Most people. Most people really don't like it. And I think it has something to do with teachers being incredibly strict about doing certain things in certain orders and so forth. What I'm going to tell you is this. I don't care about any of that as long as you follow the law of conservation of mass. Whatever goes into the equation has to come out of the equation. So whatever is on your reactant side has to be on your product side. And to make this happen, the only thing you can do is change coefficients. So if I'm looking at my equation here, a few things to simplify this, okay. Coefficients are the numbers that go in front of my elements and compounds. So there's one there, and one there. When we start out, if there's nothing written, it's always 1. Okay, it's just understood to be 1. What? 1. Okay, I'm so confused. Never mind. It's always 1. Okay. I lost my train of thought, I think. It's always 1 there. So what we can do is then change these so that the same number of atoms go into the reaction as come out of the reaction. So again, let's make my imaginary break here. And on my reactant side, I've got 1 copper and 1 oxygen. On my product side, I've got 1 copper and 2 oxygens. So this does not follow the law of conservation of mass, because somehow, as it's drawn, I magically made an oxygen as it goes through there. So what I need to do is change the coefficients so the same numbers are going in as out. So I think probably you can see what has to change here. I've got 1 oxygen on this side and 2 oxygens here. So I'm going to change my coefficient to a 2. And by changing the coefficient to a 2, I no longer have 1 oxygen. I have 2 oxygens here. Can you follow along with that? That's all balancing equations are. You just change your coefficients and make the numbers on one side match the numbers on the other side. Now, the other thing students don't like about balancing equations is oftentimes numbers get crazy and you're dealing with big coefficients and so forth. My goal is always to have coefficients of 6 or lower. So if you ever find a coefficient like 9 or something, ask me about it and I'll tell you whether or not I messed up in writing the question. But my goal is always to have short ones, so you're not spending all your time looking for what these coefficients are. You're just simply proving that you understand the concept. So let's give another one a try. All right. Oh, here's a good one. Let's do Al plus O2 goes to Al2O3. Al plus O2 goes to Al2O3. Give it a try, maybe a minute or so, and then I'll walk through how to do it. It's a little under a minute, but I don't want people to get too frustrated with it if they're not seeing it. So, questions before I start walking through it? No? Okay, so here's what I always do. I always follow 2 rules when I balance equations. First, is any element by itself is last. So here, for example, aluminum is all by itself, oxygen is all by itself. I'm going to save those for last. The reason why that is because I can put a coefficient on there and just change the number of that element and not change other ones as well. And then 2, I don't like odds. I don't like odd numbers when I'm balancing equations. And the reason for it is this. If you have an even number and you double it, do you end up with an even or an odd? Even. If you have an odd number and double it, do you end up with an even or an odd? Even. When you double things, you always end up with evens. So I always try and get rid of odd numbers to start with. So to balance this equation here, I'm going to leave aluminum and oxygen by itself. And I'm going to put a 2 in front here just to get us started. And that's going to give me 1 aluminum on this side, 2 oxygens over here, 4 aluminum over here, and 6 oxygens. So I've gotten rid of my odd number, and now I need to adjust my reactants to match. So I've got 1 here, and I need 4, so the coefficient I need to put there is a 4. That's going to change this to 4. And then I've got 2. I need to get to 6. So each one is worth 2. So 3 is going to give me 6. So my balance equation here is 4 aluminum plus 3O2 reacts to form 2 Al2O3s. And again, it's the same number and type of atoms going into the reaction as comes out of the reaction. Questions? Okay, let's try another one. That one's actually about medium difficulty for the class. I knew I'd be working through it step by step, so that's why I chose that one. Let's do an easier one to see how we do. Let's say FeCl4 plus O2 goes to FeO2 plus Cl2. Let's say 30 seconds or so. Has everyone got their ideas? Now again, this is another example of something in chemistry where you just kind of start at it and see where it takes you, and hopefully you find the right answer. But if it doesn't, just throw it out and start again. You just kind of have to work your way through that way. That's one of the reasons why I don't want to make the coefficients very big, because I don't want you guys to spend a lot of time trying to balance these out. So I've got, well, let's just see where we stand. 1 iron, 4 chlorines, and 2 oxygens on my reactant side. On my product side, I've got 1 iron, 2 oxygens, and 2 chlorines. So my iron and oxygen match up, but my chlorine doesn't. So what coefficient do I need to put in front of my Cl2 to get it to balance?
2.
A 2. A 2. That then is going to change this to 4 Cls, which then will balance out. 4 Cls go in, 4 Cls come out. 1 iron goes in, 1 iron comes out. 2 oxygens go in, 2 oxygens come out. That's a balance equation. Good with that one? Okay, let's try one more.
Would that one have been easier, or would that have been middle of the road?
This was easy.
Probably more medium ones, you think?
No, I mean, generally, when I'm writing them, I'll have maybe 2 easy, 1 medium, 1 hard, something like that.
Okay.
But it's really hard for me to know, because if you start down the wrong path, even the easy ones can seem really hard. Or the hard ones you can just see by looking at, and then you're good. So, I don't know.
Can we do one that's going to be like the same difficulty of the test?
Well, you will probably see something like that one on the test, the one we just did. However, you will also see one like the aluminum one, and let's do one more. This is actually a very, very famous reaction. This is called a combustion reaction. And we'll learn about that at the end of the chapter. But when you burn fuels like fossil fuels, hydrocarbons, and so forth, this is what happens. So C2H4, we can imagine as gasoline. It burns, so it combines with oxygen. And when you burn these things, you always end up with the same products of CO2 and H2O. So let's see if we can balance this one. This generally is a much more difficult one. I think you guys can do it, but
What's the last one you're not gonna say?
H2O.
Before that.
Oh, CO2?
Okay.
Sorry, you're getting a glare.
Yeah, from the door.
Good shadow. Say 30, 40 seconds. Just. Okay. So to go about balancing this, we break it in parts again, and then we just count up what we've got. We've got 2 carbons, 4 hydrogens, and 2 oxygens on our reaction side. 1 carbon, 2 hydrogens, and 3 oxygens on our product side. So now it's just really a matter of trying different things and finding out what works. I'm going to put a 2 here first, which then is going to make my oxygen be even, is why I'm doing that. So doing that, that's going to change the amount of hydrogen I've got to 4 hydrogens. And I've got 2 oxygens here and 2 oxygens here to give me 4 oxygens. Yeah?
Where'd you get the 3O from?
Oh, so I have 2 here, and then I've got 1 over here. So that will give me 3 total.
So just always
So-
combine them and not make them separate when you're doing your, like instead of like having 1 carbon, 2 oxygen, 2 hydrogen, and then another oxygen, just put them all together.
I guess I always put them together. I don't know that it really matters as long as you keep track of the whole total.
Okay.
It may actually be easier the other way, but I've never done it that way. I don't know. Yeah.
Okay, so you have 2 oxygens on this side, 3 on the other side.
Mm-hmm.
And you said putting the 2
Putting the 2 in front of the water.
balances out the hydrogen.
No, it's not going to balance it out. It's
Okay.
going to make, poor choice of words there, that was my fault. It's going to make it an even number of oxygens. So I had 3, but by putting the 2 there, it gives me 4.
So then we have to change the other side, right?
We will have to change
Okay.
the other side. Absolutely. Okay, so on this side, then we have 4 hydrogens on both sides. We only have 2 oxygens there, and we have 4 here. So what would I put here?
A 2.
A 2.
a 2, that then is going to change that to 4. But with that in mind, is it balanced at this point? No, it's not, because my carbons aren't equal. I have 2 carbons over here and only 1 over here. So I'm going to put a 2 there. That then is going to make 2 carbons, but it's also going to change my oxygen. So 2 times 2 is 4, plus the 2 now changes to 6 oxygens. 6 oxygens by putting a 2 in front of CO2 there.
So that, but it still doesn't make it balance on this side, right?
It still doesn't make a balance on that side. You're right. So I have 6 here, I only have 4 over there. The carbons match, the hydrogens match, but I've got 6 oxygens and 4 oxygens, so what do I have to do?
Change it to a 3.
Change that to a 3, which then changes that to a 6. So looking at it, it looks to be balanced. However, you just have to go back and forth until they're all equal to each other. So the last thing I'm going to always suggest that you do is just recount it. So there's going to be 2 carbons, 4 hydrogens, and 3 times 2 is 6 oxygens. Over here, 2 carbons, 4 and 2 is going to be 6 oxygens, and 4 hydrogens. Okay, so that ends up balanced in this case. And really, your thought process there is exactly right. Okay, I changed this. Well, that's going to change something on this side. So I need to change something on this side to match. And how does that affect the other side? And just going back and forth. And that's really the only way to do it. But you can see how that one's much more involved than the previous examples we did.
Yeah, well, you always start out with, when you're trying to do it, like you said in your second rule, you did like the odd numbers. You always start with 2 of something and see how that works out.
I do.
And then, because that led us to obviously still realizing that it was not quite enough. So then we move your 2 to a 3 then.
Yeah. You've got to pick somewhere to start.
Right?
And I always just pick an odd number to start because it's easier to get to evens than odds. So I just pick one and I change it and I start jumping back and forth doing it. I wish there was a way that I could say, like, you have to put a number in the second slot and then go back and change the first slot and then go, but it doesn't work like that. You just start doing it and then you get there. Okay. Let's try one more.
Now the problem we just did, you said it was combustion.
Combustion.
Okay.
Yep, that's the name of that. And later on, it'll be after the exam, we're going to talk about combustion specifically. It's one of the basic types of reactions that will occur. Yep. So let's do NiCl4 plus O2 goes to Ni O4 plus Cl2. So NiCl4 plus O2 goes to NiO4 plus Cl2. So balancing this one, we'll do exactly the same as we did before. I guess let's do it this way. Anyone feel brave and want to share what they got?
NiCl4 plus 2O2 is equals to, or goes over 2, yields NiO4 plus 2Cl2.
Okay, does anyone disagree with that? No? Okay, going through and counting it. We're going to have 1 nickel, 4 chlorines, and 4 oxygens on our reactant side. And then on the product side is 1 nickel, 4 chlorines, and 4 oxygens. So it's perfect. Okay, so that's a balanced equation then. The same number and types of atoms go into the reaction as comes out of the reaction. And this is the fundamental rule of the law of conservation of mass, actually. This says that. So now that we understand balanced equations a little bit, we can actually discuss what's called stoichiometry. Now, stoichiometry is a really, really fancy word for ratios. It's just the coefficients in a balanced equation. And what that means is, say we look at this equation here. What this means is that for every 1 mole of NiCl4 and 2 moles of O2, this yields 1 mole of NiO4 plus 2 moles of Cl2. So the coefficients in our balanced equation just tells us the ratio between moles. So if I start out with 1 mole of NiCl4, how many moles of NiO4 can I make?
You only start out.
If I start out with 1 mole of NiCl4 and a whole lot of this, okay, 1,000 moles of this, how many of these can I make? See, that's going to be confusing too. Yeah. 1. Okay. So let's get this out of the way right away. If you've had a high school chemistry class and you learned the concepts of limiting reagents, we're not doing that in this class at all. Okay, so you never have to worry about limiting reagents. In all of the questions for this class that are going to be asked and so forth, you always have exactly the right number of everything else. You don't have to worry about, do I have too little or too much of something else not listed? Okay?
But I thought that was basically like what stoichiometry was.
Stoichiometry can tell you how much you need of something, but in terms of this class, I don't want to get into the whole idea of running out and then that defining something else, because basically that automatically turns any problem into a 3-step problem, because you've got to calculate 1, you've got to calculate 2, and then you've got to compare and then calculate 3 off of whichever one, which I don't want to do here. Okay? So if you want to, yeah, don't do it. Okay. Yes. Okay, so if I have one of these and exactly the right amount of this, I can make one of these. Right? That's what my balance equation is telling me. So if it's a 1 here and a 1 here, for every one of these I start with, I can make 1 here. If I start with 1 NiCl4, how many Cl2s can I make? 2. 2 now. 2 now, because it's a 1-to-2 ratio. If I start with 4 NiCl4s, how many Cl2s can I make?
2.
2. So if I start with 1, I can make 2, right? That's what we said before. But now if I start with 4, how many can I make? What? Why would it be 2
If you start with 4,
if I start with 4?
So the number in front of the 2 has to change.
so it'll be 8, right? 8. So
Yep.
that would be 8. And
Why would it be 8?
no, it would be 4.
It's
Because
4.
that needs to be 8. No, it would be 4.
Okay, so let's look at this. Okay. What is the relationship between the two? It is that for every 1 mole of NiCl4, I can make 2 moles of Cl2. Do we all agree with that? Yes?
Yes.
Okay, 1 to 2. So if I start with 4 moles of NiCl2, and I want to find how many moles of Cl2 I can make, I need the relationship here to do that conversion. Well, this is what stoichiometry is. It's the conversion between them, the ratio. So is mole NiCl4 going to go above my line or below the line?
Below.
Okay. So 1 mole NiCl4 is going to go below. 2 moles Cl2 goes on top. NiCl cancel, mole Cl2 match. And now doing the math, 4 times 2 is 8, divided by 1 is 8. So if I start with 4 moles of NiCl4, then I can make 8 moles of Cl2. And that's what this ratio is telling me. Yeah.
Is that a 1 on the, or 2 on the top?
It's a 2. 2, yep. And stoichiometry can be used like this for all these different parts. So let's have another question. Let's say, how many moles of O2 are needed with 7 moles of NiCl4? So how many moles of O2 are needed to react with 7 moles of NiCl4? So do exactly the same thing we've been doing with unit analysis. That doesn't help. Exactly the same thing we've been doing with unit analysis this whole time, and see if you can figure out the problem. Say 30 and 15, 20 seconds. See if you get your idea started. If you don't have the actual math, that's fine. Okay. Questions before I start working through it? So, in the unit analysis approach, what is given to me to start with in my question?
7 moles.
Okay, so 7 moles of NiCl4. And it's asking me to find moles of O2. So I need a relationship between the two. Well, this is the third conversion that we're learning in this class. Converting between moles of one thing to moles of something else is always done with stoichiometry. So you always have to have a balanced equation to convert between moles and moles. So looking at this then, I'm going to relate this one and this one in this case. So 1 mole NiCl4 goes on the bottom. 2 moles of O2 go on the top. Moles NiCl4 cancel. O2 match. 7 times 2 is 14 divided by 1 means that I need 14 moles of O2 to react with my 7 moles of NiCl4. Because for every 1 mole here, it takes 2. So if I have 2 moles, it's going to take 4. 3 moles is going to be 6, so forth and so on. 7 would be 14 in that case, because it's a 1-to-2 ratio. Yeah?
Will it always be the 1-to-2 ratio, or does that change based on what's in the?
It changes based on what's in the balance equation. You're exactly
So
right.
if it was like 3 or something, that'd be 3 to 1.
Yep. So if, for example, this was, just to be an extreme case, 27 and 32, then you would just carry those numbers down to 27 and 32 or whatever it is. Yeah, it won't be 27, 32, but. Other questions? So this is just telling us the ratio for which these react together. Let's do one more quick, and let's go back to an earlier reaction we had that was 4Al plus 3O2 reacts to form 2Al2O3.
Another balance.
This one is balanced. Yes.
On the exam, will it always be part 1 is balanced and part 2 is converted? Or will you give us a balance one, you'll just ask us to convert it?
Both.
Both. Okay.
There will be cases where the first thing I'll have you do is balance it, and then there will also be cases where it will already be balanced.
Okay. And then you label those, and those are what go into your relationship in the center part when you're trying to
The
convert one to
conversion.
another.
Yep. So here then, how many moles of Al2O3? Actually, this. Sorry, you're writing wrong. How many moles of Al are needed to form 5 moles of Al2O3? How many moles of aluminum are needed to form 5 moles of Al2O3? So let's take a minute, minute and a half. Everyone have their ideas? Okay, so to work through this, 5 moles of Al2O3 are what's given to us, and it wants us to find moles of aluminum. So, just like always, we need a conversion here. Well, we're going from moles of one thing to moles of something else. So that's going to be stoichiometry. And looking at our balanced equation, 2 moles Al2O3 is going to go on the bottom. 4 moles of Al goes on the top. These cancel and it matches. You guys see how unit analysis pays off here? Keeping track of what goes where and so forth. It's really useful. So now 5 times 4 is 20 divided by 2 is going to be 10. So to form 5 moles of Al2O3, it's going to take 10 moles of Al.
Okay, so you took the, I'm sorry.
No, go ahead. Yeah.
So you took the 4 that was in front of the AL and just made it the process.
Yep.
Okay.
And that's exactly what you do.
So I was looking at this and I was thinking, I guess my thought process would be if you have your 4 ALs and you have your 4 ALs over here, wouldn't there need to be a 2 with your oxygen on the other side?
Well, we're just finding AL, not oxygen though.
Would that make sense or no?
To where?
On the other oxygen, so Al2,
Over
2O3?
here?
Yeah.
No, because this 2 is for the whole thing. So it's a compound.
got
It gets
it.
carried through. Yeah.
Okay, so I did it wrong because I did 4 over 3 in the brackets. And
Okay.
You got the 2 from the AL.
Yep, the 2 goes with here. So whatever your species is, so it's moles Al2O3, means that you've got to use the number right in front of that. So if this would have been O2, for example, then it would have been the 3.
Okay, so I don't know.
Yeah, I didn't.
Will it work? Because I've just been doing it like I first couple times I wrote it down, but I don't know. I feel like I'm working the way to do it in my head. So will it always work? Because the way I do it is I look at we're just only looking for AL. So in the problem, I kind of like eliminate O3. I mean 3.
Okay.
I mean yeah, O3, and I just look at how in the problem we're putting 5 next to it. So 5 times 2 would be 10. So I know that we would need 10 next to the AL because AL is by itself. Would that work all the time, or would you always have to? I don't know. Do you get what I'm saying, though?
I think you're trying to do it using ratios. And yes, it will work. However, it gets very confusing. And when we do a second step off this, it really gets confusing.
Okay.
So if you can follow it in your head and you're getting the right answers, more power to you. But I don't know that I could do that. So be forewarned there. Okay, that's it for today. We're going to do more of these next time. As you guys are practicing, I would highly encourage you to pull up the old exams and see these types of questions so you know roughly what type of questions. I'm not going to change the types or anything like that. So if I wrote a question like it on the old exam, you'll probably see it on the exam you guys are going to see. Okay, grab candy on your way out if you want some. Make it disappear so I don't have to take it home.
Got that. Okay.
And enjoy your day.